Welcome to ECE 302. This is lecture 5.11 on principal component analysis. I'm Professor Stanley Chan. In the previous lectures, we talked about random vectors, and we talked about the joint distributions in high-dimensional space. Two things that we have been paying a lot of attention to. One is the mean vector, the other one is the covariance matrix. And we talk about a very special type of high-dimensional distribution, which is the Gaussian distribution in high-dimensional space. We drew a lot of pictures to understand the shape of the Gaussian distribution. And we say that in order to understand the shape of the Gaussian, we need to look at the eigen decomposition of the covariance matrix. So today's lecture is an extension of that. We're going to look at one application of the eigen decomposition of the covariance matrix, and that is this topic on principal component analysis, or PCA in short. So what is PCA? To many of you, PCA is a very mysterious technique in data science that somehow compress the data into low-dimensional space. But essentially what it is, I summarize this PCA using this simple statement. It is the eigen decomposition of the covariance matrix sigma. Now, in case you forgot what is a covariance matrix, the covariance matrix sigma is the expectation of x minus mu and the x minus mu transpose. And you take the expectation over all the possible x. And here, certainly, x is a random vector. That's how we compute the covariance matrix. And then, what do I mean by eigen decomposition? If you apply eigen decomposition on this covariance matrix sigma, you will be able to obtain a matrix U with certain property that U transpose U will give you an identity matrix, and therefore we say that the columns of this matrix U, they are orthogonal and they have unit norm. So if you apply the eigen decomposition on sigma, you will be able to get this matrix of U, and then you will also get another matrix S, or sometimes I call them lambda. This S matrix is a diagonal matrix that stores all the eigenvalues of this matrix. So if you apply the eigen decomposition to sigma, you will get U and S. They are matrices. Mathematically, you can also say that sigma can be written as U, S, and U transpose. And this is what we mean by decomposing a matrix sigma into U and S. So PCA is what? PCA is exactly this decomposition on this covariance matrix sigma. So now you may wonder, how can this ever be useful? Well, the usefulness of the PCA is that you can look at the columns of this U matrix, and then you can look at the coefficients that will be used by this U matrix. Now, this may not be very clear at this moment, but just think about that. When you have any vector, you can write it as a linear combination, I going from 1 and certain dimension d, of some coefficient bi times your ui, where ui is one of the columns of this matrix U. So essentially what you're saying is that for any data point x, I am going to express it as a linear combination of my eigenvectors. These are what people call them the basis vectors. So you're doing a decomposition of the signal into bases. And then by looking at, instead of looking at the x, which could be a high-dimensional vector, all you need to do perhaps is just to look at the coefficients that are representing this data point x. And usually this d can be a lot less than the number of elements in this x, and therefore you will be able to do a data dimension reduction. So that's the whole idea behind this principal component analysis, which is essentially an eigen decomposition of the covariance matrix sigma. And following that, you are going to do a linear combination of the bases to represent a data point. All right, so at this moment, everything will still be very fuzzy. And I'm sure that you have come across this PCA in other places. And so what I want to do today is to talk about the details about this PCA to make sure that you understand the basic ideas. Okay, so to start with, let me describe this problem setting. Imagine that you have a set of data points, x1, x2, and xn. Now I put these indexes at the top as a superscript to denote that they are the data points. So you have the first data point, second data point, the third data point. The way to think about this is that you have a data set, you have data point 1, 2, 3, and so on. This data point can be a vector which contains x1, x2, and so on, xd. And then this, I call them x1, I put a bar over here, and this is the first data point inside this data set. And then this is another data point, x1, x2, xd, okay? And then this is the second data point, x2, all right? So now in order to make sure that they're different, of course I put a 1 over here. And then this is a 2. Okay, so this 1 and 2, they denote the data points, and then the subscripts, they denote the elements of this vector. Okay, so these are the data points, and you can imagine that you have a set of images, and all the images you can store them as a long vector, and so every element in this vector will represent a pixel value. Or you have a speech file, every element there will denote the signal at that time stamp. So these are the data points in your data set. And then you imagine that you suppose that all these data points are living in a high-dimensional space where we assume that each xn is living in RD, meaning that it has d elements. Now, your goal is to find a low-dimensional representation in RP where p is less than d. Now, how do you do that? Look at this equation here. This is your nth data point, xn. I am going to represent it through some basis vectors. This is a vector, I call it a vi, and then I have a p of those. Certainly in this principal component analysis, we need to find out the v. But imagine that in this moment, that v is given to you. Then what do? Well, you go back to this equation here. For every vi, you multiply a constant. It is a scalar. It is alpha I. Okay, so for the ith basis vector, you have the ith scalar coefficient that goes with vi. And then you take the sum of everyone. So you can think that, let's say I have v1 being this vector, and then v2 being that vector. And then you say that alpha I, so you have alpha 1 and alpha 2. Let's say alpha 1 has a length. When you multiply them, that will just extend the v1 vector as alpha 1 v1. And then you have another alpha 2. Maybe alpha 2 is here, so this is alpha 2 v2. And then the sum of these two vectors will give you a vector like that. So you can do a propagation here, and then that would be your vector, and so the overall vector would be this. Okay, so this blue vector is alpha 1 v1 plus alpha 2 v2. Okay, where v1 and v2, they are vectors. Okay, so you see that for any data point xn, I can represent it as a linear combination of these two basis vectors. Now, what is this n? This n, of course, has to be corresponding to the nth data point in my training set. And so if I have n, capital N number of data points, then for everyone I will have this small n as the index. So you ask, what is the benefit of writing xn as here? The benefit is that if you can approximate xn as these linear combinations, then VI's are usually known to you. So you do not need to store anything for the VI's. All you need to remember is that xn can be fully represented by these two coefficients. Why? Well, if you know this VI, V1 and V2, and if this is my x is represented as this, and you know V1 and V2, then you really do not need to know what x is. You just need to know the combination weight. As long as you know the combination weight, and since you know V1 and V2 already, you will know x. And therefore, if you have a very, very long vector, and this is your long vector, and I say that this long vector can be represented as alpha 1 times alpha 2 times another vector, you do not need to remember this vector anymore. Since this is known, as soon as you know these two coefficients, you will know how to represent xn. So this is what we call the low-dimensional representation of a high-dimensional vector. So every xn in this RD can be represented by, and this is a vector at alpha n. So now it becomes a vector. So this alpha n will contain all the alphas, alpha 1, alpha 2, and so on, alpha p. Okay, and so now you can imagine that, let's say I have a set of data points, they are marked by the blue crosses, and then what I want to do is that I want to find the VI's and also find the alpha RNs so that I can best represent them. By best representing them, I mean that I can draw this principal components, one here in this direction and one here in this direction, so that I can capture the signal. All right, so let's do some calculations and see what we need to do. Let's consider the simplest possible setup where I give you one data point and then I ask you to find the principal direction. In other words, I have a vector x here, and then I ask, how can you solve this problem where you say x is approximately equal to summation of alpha I and then vi, I going from 1 to p. I need to find, I give you the x and you need to find alpha and v. And then, of course, this is an ill-conditioned problem because you may have more variables than the number of observations. But that's why I would just say that d equals to 1. Okay, so I ask, how can you write this problem as the following? So I need to find the alpha, find the v such that it is approximately equals to x. Now the problem is also not just like this, because if everything is unconstrained, then you would just say that alpha is 1 and v is x. But let's also say that the norm of v is 1, because in this eigen decomposition problem, we know that the U matrix, the eigen matrix, every column vector has a norm of 1. So let's also put that into our constraint. Then we ask this problem. We want to minimize the 2-norm square between x and alpha times your vector, and I need to solve for both v and alpha. So what is the solution to this problem? Okay, so let's first assume that v is available. Then you can take the derivative with respect to alpha. Then you will get to this equation. So you take the derivative of this function. So d of d alpha of this function, which is x minus alpha v square. Now note that this is a vector equation, but nevertheless, this thing is just norm of x square minus 2 alpha of x transpose v plus alpha square of v square. So it is actually just a quadratic equation in alpha. Right? So if it is a quadratic equation alpha, I know how to take the derivative with respect to alpha, and that will give me this equation, which is 2 times, right? So if you take the derivative with respect to alpha, you have 2 times this guy, and then 2 times this guy. So that is equivalent to saying that you have this equation. And then if you equate it to 0, you can show that alpha will equal to x transpose v, and that is my alpha. Okay, so for at least for this one sample problem, we can determine this alpha. Alpha is v transpose x. And then what? Now, and then we want to substitute this alpha equals to x transpose v into the equation again, right? Because in the previous equation, I need to solve for alpha, and then since I know what alpha is, I can just substitute the alpha. So the equation goes as follows. So you want to minimize the deviation between x and your alpha v, which is your predictor. We can expand the term as here. You have x transpose x, x transpose v, and v transpose v. You have alphas here and there. But note that since you're minimizing over v only, since you're minimizing over v only, then this term does not really matter. Okay, so this term you need to keep it here. So you have this term. Now, what else? What else is that? And this term is actually 1, because you have this constraint where the norm of v is 1. So you have what? You have this minus 2 alpha times x transpose v, and then you have alpha squared. Then you substitute your previous calculation where alpha equals to x transpose v into the equation by replacing this and that. Then you have this equation, and you can simplify things. You can get to what? You can get to x transpose v squared, and that's a minus. Okay, so this is the solution that you're obtaining from here. And of course, if you're taking the mean, that you can flip the sign over if you have a minus sign, so that will become a max. And so this max problem becomes argmax of x transpose v squared, and then you want to find the v equals to 1. And this problem is the same as if you just write out the detail is v transpose x, and then x, and then you have v. Okay, so because this is a scalar, this is another scalar, so when you multiply everything together, you will get back a scalar. So that's not a problem. That's why we will end up with this equation. So it says that this minimization problem is equivalent to this maximization problem in terms of v, where x is a known vector. Now, finally, what we are going to do is that we are going to take the expectation on the optimization problem, because we know that x is a random vector, and so we can take the expectation over. Then we know that expectation can go inside, and let's see what is this. If you assume that the x vector is a zero mean, then this is really about a covariance matrix, sigma. Okay, and therefore, what you will end up having is the following. This problem says that if you want to find one principal direction for one data point, then the solution is given by the optimization of this thing. If you have many data points, and if you take the expectation of all the possible x over here, then your solution will also be the solution of this maximization problem. And this maximization problem is exactly the same as the one that leads to the eigen decomposition result. The theorem here says that if you have this sigma being a d by d matrix, and then you have an eigen decomposition, you can write it as sigma equals to u as u transpose, then this optimization problem will have a solution that v hat, which is the solution of this problem, is given by ui. Now, this is not true for any I. This will only give you the first one. Okay, it will give you the first vector. And then now you can knock out this the first vector, and then you can say that not only that I want to find this criteria, I also want to make sure that my V is orthogonal to the vector that I have already calculated. Then you solve this problem again, then you can get a second eigenvector. So this theorem basically gives us a way to link this optimization problem to the eigenvalue decomposition of the sigma matrix. So what is the implication? Well, the implication can be seen by looking at the finite sample case. By finite training sample case, I mean that you are not only interested in one x minus alpha v, you're not only interested in this, you are interested in looking at this sum of all the possible training samples. It seems you're taking this finite average, and we know that this is the average, right? Average is approximately equal to the expectation, and therefore the expectation will really tell us something about the expectation will really tell us about this matrix inside, which is x transpose, and you take the expectation. So in practice, you can approximate the sigma by this empirical estimate, which is this term. This is the correlation matrix. In addition, you can also subtract the mean. If x is not zero mean, you can subtract the mean. This is called the centering process, and that can also allow you to do the principal component analysis. So this is a uncentralized version. This is a centralized version of the PCA. All right, how do we interpret this problem? This problem, as you recall, all we are doing is to find at alpha and a v such that it minimizes the difference from x, and therefore it is an approximation of the x. And so if you take the expectation, you are enumerating over all the data samples in your training set. So if you solve this problem, and we show that this problem is equivalent to this problem, and therefore we're solving this eigen decomposition problem, then pictorially what it means is that you are really trying to find the one that can maximize the variance. Why? Well, because this is a scalar, and then you're finding a v that can make this variance as big as possible, because the covariance matrix is telling you something about the variance. On the picture, you can see that if I have all these blue crosses as my data point, I am really trying to rotate, right? Because v is the principal vector. So if I say that v, my principal vector is here, and then this is the minor axis. If I draw these two v's as follows, will I be able to maximize the variance? And the answer is no, because you're not aligning well with the data. Is this a good option here? This is also not a good option here. This one is a very good option. Why? Because you're finding a v, v1 and v2 that can make the variance as big as possible. And so big variance means signal and small variance means noise. And so you are trying to maximize the descriptive power of your data by finding the right major and minor axes. So how can this principal component analysis be useful? Let me show you one application here, which is the eigenphase problem. The eigenphase problem is a very famous problem about 20 years ago. It is about recognizing the phase using a low-dimensional representation. So imagine that you have a data set that contains n data points. Each data point it is an image, and you can store them as vectors. And so it is a d-dimensional vector, and then they have the each of them is a root d by root d image. And then you can take a low-dimensional representation, which is this lecture, and then we can usually we have two tasks. The first task is to find a low-dimensional representation, which is about this lecture, and then we can do a classification of a new image in the later lecture. So this PCA is really applied to here. I can try to compute the principal component, and then for every image, let's say this image, I can say that it has these two major components, and I can instead of you looking at a 1,000 pixels here, I may just need maybe 20 coefficients to represent the same image, and from that you can compress the signal to a low-dimensional space. So how do we do the low-dimensional representation of all these images? First of all, you compute the mean vector. That will give you this mu. And then we can compute the covariance matrix. This is the empirical covariance matrix that can also be computed from the data set. And then I apply the eigen decomposition, do a USU transpose to this sigma matrix. And then the next one would be the magic, okay? So let's say I have a new image Y, okay? An image that has not been inside the training set. I take this image, I call it Y, and then I can compute the coefficient. The coefficient is defined as here as the UI transpose Y. Okay, so let's say I have a new image Y here. I can extract all these alpha 1, alpha 2, so alpha D for this input data Y using U1, U2, and U3. And then you can just do a transpose of the Y's, transpose of the Y, transpose of the Y's. That will give you the coefficients A1 through AD. And then instead of describing this vector can be a very, very long vector. And then here you may only have a few coefficients that can be as descriptive as the entire long vector. Some of you may wonder, in this setting, how many coefficients do I want to keep in order to make it a low-dimensional representation? Normally, you can plot the eigenvalues, and then you can look at the eigenvalues. You can look at the distribution of eigenvalues, and then you can set a cutoff somewhere in the middle. And let's say I want to make sure that this area covers 90% of the signal. Then you can determine this point. Or you can say that I want to go to this point where this y-axis, this value is less than a certain number. So that can also help you set up the cutoff. Usually the cutoff is not too big number. This orange line is usually not a big number because typically these eigenvalues of many data sets, they will drop down very, very quickly. Unless your data sets are very, very diverse. For example, if you have an image data set for a face, usually the faces, they are very similar, and therefore they can be described by the first few eigenvectors of this covariance matrix. And as such, you only need to use very few coefficients, and that will be enough to describe your data. In practice, what do you do? This diagram shows you the practical flow of how do you compute the basis vectors as well as the principal component analysis coefficients. Let's say you have a training image. Okay, so this is training image. You can train to obtain this U1 through UP. Okay, so these are obtained by the training set, and then the shape of your eigenfaces are shown as here. Now we can take a look at these images. They actually make some sense. This is the baseline image, which is sort of like an average of all the faces in your training set. This is getting into something like a high, some derivative version. And then this is very, very high frequency variation, some texture details of your face. So as you go from here to there, go from here to there, you are seeing more and more detailed textures as opposed to the top corner where you see some of the baseline signals. So this is the training set where you are able to obtain all the use from the eigen decomposition of the covariance matrix. Now, During the testing, let's say now this image becomes a testing, then what you do? Well, if you're running a testing, then the U1 through UPs, they are already fixed. Then all you need to do is to determine these alpha 1 through alpha p, and the alpha 1 is all the alpha i's, as we have shown before, alpha i's is determined by a ui transpose your data. Okay, so in this case it would be your y. That will give you all the alphas. And then once you obtain all the alphas, then instead of using the entire long vector of y, you just need to say that this image can be represented by this p element vector with alpha 1 through alpha p. So then you can take this alpha 1 through alpha p for your downstream processing. For example, you want to recognize faces. Instead of using all the pixel values of y, which is a very high dimensional vector, you can use a much lower dimensional vector of alpha 1 through alpha p, and they carry on almost all the same information, except some truncation due to this eigenvalue that you removed. So this is the basic idea of principal component analysis. And there are many details that you can find in our ebook, and as well as on the internet. There are many tutorials about the PCA. However, I hope that you can just remember a few major ideas of the principal component analysis as you navigate through this big literature. PCA, remember PCA is a dimension reduction tool that can turn a raw data vector in d-dimensional space into a much smaller, we call them the feature vector alpha in RP. P is of course much smaller than D, for otherwise you're not achieving this dimension reduction. The whole idea of PCA, as I have been emphasizing over and over, is to run the eigen decomposition of the covariance matrix. And then the rest is just to project your observation vector y onto the space spanned by these eigenvectors. There are limitations of PCA. If you ever think that PCA is so powerful that you can handle all kinds of problems, that is not true. PCA, just like any other data science techniques, they have limitations. Here I'm summarizing 3 of the limitations that at least I have been seeing over the past few years. One is that PCA fails when the raw data is not orthogonal. Here is a diagram illustrating the situation. Let's say you have the blue crosses. They are living as here. This one you can find the principal component with the black axis and also the yellow axis. Now, certainly the yellow axis is not perfect, but at least it can describe the data. If you have a data set that has a distribution like this, which is living on the circle, then when you draw the black and also the orange, you will not be able to classify them. You will not be able to do this PCA, and then you're not able to say that this data point is mostly represented by this principal component. You just do not have this notion of principal component because it is not really orthogonal. The data set itself is not orthogonal, so that the PCA, no matter how you do the PCA, is not going to work. You cannot find the major and minor components. Now, the second point is also very important for anyone who is doing data analysis, which is that the bases returned by the PCA are not very interpretable. One example is the eigenphase here. Now, of course, I can argue that the base image, this is more like an average image, and here it contains more textures. But beyond that, are you able to say that how different is this image compared to this image? These are all the basis vectors. And there aren't that many interpretations that you can offer from here. It's unlike other techniques where you can say that here is an image, and then so you have you have the eyes here, and then there's a nose here, and then there's a mouth here, and then there are hair over here. It's not like that kind of decomposition. And so the PCA actually returns you something that's purely data driven. It's purely based on the covariance matrix, and you are not able to do this part-based decomposition or local features. You're not able to do that. You're just obtaining whatever the data set gives you. So the basis returned by PCA is not always interpretable, and that's a big limitation if you try to use PCA to offer you something useful. And then the third point is that PCA does not return you the most influential component. One example would be that you run a medical data set, and then you see height, weight, BMI, etc., etc. You have many columns of data. You say that I have redundant features, and so I run PCA. I have 20 features. I don't like them. I only want to keep the leading 5 features, and I run the PCA. You do that, and then I ask, then what are the 5 leading components? What are the meaning of the 5 leading components? And then you say, okay, these are the numbers. But 1, they're not interpretable. And 2, even if you know that these are the most influential ones, you don't know what they are. So it does not tell you which component among the 20 components that you have. Okay, so let's say this is a weight, height, BMI, and so on, and these features. When you run the PCA, you will only have basis vector 1, basis vector 2, basis vector 3, and you say that these 3 bases are the most influential ones, but they just do not correspond to weight, height, or BMI, and so you do not know whether height, weight, or BMI is contributing to your principal component. You don't know that, and therefore PCA has a fundamental limitation of it doesn't tell you anything that you want to interpret. However, it is still a very useful tool for you to compress data. For example, in the image classification case, where if you can compress the dimension to a low-dimensional space, that is still a very useful technique. But as you use the PCA, just bear in mind that it has other limitations. All right, so this is a very practical lecture. I hope you have learned something useful. Obviously, we are not covering the entire aspect of principal component analysis, and that's also not the motivation for this lecture. The goal of this lecture is to tell you the basic ideas of PCA so that you can search for the literature on the internet and other places to have more experience on this PCA. All right, so I hope you find this lecture interesting, and I hope to see you again on this video channel. Thank you very much.